if you guys could answer these 3 questions in your science journal from our last kind of unit that we looked at. How long is a day? How long is a year? How long is a month? Why do we have leap year? Your bell work for today asks you guys what this was a photo of. And judging by past years, there's been a number of answers as to what this could possibly be. All right. First one, maybe it is a giant oil spill. Obviously, it's kind of dark in color, looks like a big, huge oil spill. Maybe it's smoke from a forest fire, or from a volcano, or something else that is burning. Had a few people think that it might be a black hole. What this actually is a shadow. You might think, what could possibly cause a shadow that big on planet Earth? Is it aliens? Nope. The answer is our moon. And if you are standing on the surface of planet Earth, and you're standing right here, you can still get full amounts of sunlight. It is completely daytime. However, you guys know that when you go into a shadow, it gets much darker. So if you are in the shadow of the moon, daylight's going to go away, and it's going to be almost as though it is nighttime. There's no other light from anywhere else other than our sun coming down to hit planet Earth. This is a shadow. We call it an eclipse. So we're going to talk about eclipses. There are different types of eclipses, and we're going to talk about one of them today. New questions of the week. I would like you guys to write these down in your science journal. Question number 1, what are eclipses and what conditions are necessary for them to occur? Question 2, why does the moon look different at different times? I'm going to start off, I'm just going to show you guys some cool pictures of eclipses. This is a time lapse of what we call a lunar eclipse. This is another time lapse of a lunar eclipse. You can see that the moon looks like a normal moon, then it starts to be covered up. All of a sudden it turns red. Some people refer to that as a blood moon. And then you start to get the regular looking moon back. This is what we would refer to as a solar eclipse. This is actually the type that we're going to look at today. This is a total solar eclipse. That would be a partial solar eclipse, because only part of the sun is covered up. This is a total solar eclipse because all of the sun is covered up. This is a solar eclipse taken from the International Space Station, looking down onto the surface of Earth where there's a giant shadow of the moon. If you are a human that is living in this part of the Earth, you're going to be looking at a solar eclipse. Earth is not the only place that can have solar eclipses. Other planets have moons, and so if you were somebody who lived on Jupiter, and you just so happen to live in this little area on Jupiter, you would be actually seeing a solar eclipse. The moon of Jupiter, I believe that's Io, based on its crazy colors, you're going to have a shadow of that moon falling on the surface of Jupiter. So you would see a solar eclipse if you were living right there. How do you create a solar eclipse, and why do we not get them every month? That's what we're going to look at today. In your science journal, 2 brand new pages that are facing each other. Create 3 sections. And you guys are going to have one page all by itself be section number 1. And the next page that is facing that is going to be section 2 and section 3. We're going to fill out 1 partially today. We're going to fill out 2 all the way today, and we're going to fill out 3 tomorrow. Section 1 are going to be a couple vocab words. Words that you've probably never seen before. So what I want you to do is write these words down and leave a blank space in between each one of these words. And as I go through talking about eclipses, I want you guys to write down what the definition is. Let's figure out how eclipses work. You have a light source out in space called the sun. It is the only light source that hits Earth. Yes, there are stars, but they send us such little amounts of light that they're not going to light Earth up in any real way. Even moonlight isn't light from the moon. It's actually sunlight that's bouncing off of the moon down to Earth. This is going to represent the sun, and then we have our moon. This is the surface of planet Earth. If I was going to create an eclipse in our room on this wall, I would have a single light source, and I would have something to cast a shadow, and then I would have a surface that shadow is being cast on. We're going to learn a new word, and that is umbra. It's a weird word. It's really only used in astronomy, but umbra is Latin for shadow. And so if you have a shadow falling on the surface of a planet, you are in the umbra. If you are looking at a total solar eclipse, you are in the umbra. What if you don't fall in this complete shadow? You fall in this shadow here. That's where part of the sun is being covered. That is what's known as the penumbra. You put P-E-N in front of it. Penumbra means a partial shadow. Because if you're standing here, part of the light is being blocked by this soccer ball, but not all of it. You can still see part of this light bulb. Another thing that you guys need to know is that our moon orbits in an ellipse, which means sometimes it's closer to Earth, sometimes it's farther away. If it's closer, it's going to look bigger to us. If it's farther away, it's going to look smaller. So if our moon is farther away, it's going to look smaller. If our moon is closer, it's going to look bigger. If our moon is farther from the surface, we could actually represent that by having a wall that is farther from the moon. The surface of this wall is farther from the moon, just like the surface of Earth is going to be farther from this moon because the moon is farther away. And if that happens, the shadow of this ball never quite reaches the surface of that wall. Instead, the entire wall is all in the penumbra. The entire wall is having a partial shadow cast on it. You can see part of this light source no matter where you are on that wall. I'm going to try to recreate an eclipse so you guys can see it. Got a moon, have a light source. It's actually the projector, which you guys cannot see. So the light source is coming from behind where you guys would be sitting. And then I have the surface of planet Earth. The sun is hitting planet Earth, and we have our moon. Here comes our moon. Pretend that my shadow is not here. Here comes the moon, and we are going to have a shadow of the moon. This is the umbra, in the dark part of the shadow, and it's difficult to see because it's not a huge distance involved. It's inside of a classroom, but there's a little fuzzy line right along the outside of this shadow. That fuzzy line would be the penumbra. If you were a little tiny thing that was living where that fuzzy line is located, part of the projector's light would be covered, part of it would still be hitting. So it's still in shadow. It's not, the shadow though is not as dark. This is the umbra, the shadow. This is the penumbra, the partial shadow. This is what we would refer to as a solar eclipse because the moon is blocking the sun. Whatever is being blocked, that is what type of eclipse it is. So what you guys need to know, that if the sun is being blocked by the moon, you have a solar eclipse. If it's being blocked, it's casting a shadow on planet Earth, and that shadow is known as the umbra. If you're over here, you're going to know, or you're going to see, what is a partial eclipse. Part of the sun is being covered up, so it's not going to be quite as bright. You're going to be in a partial shadow. We also just learned that the moon is not always the same distance from Earth. So if we have the moon happens to pass in between the sun and Earth while the moon is close, you're going to have the shadow fall on Earth. However, if you have the moon cross in front of the sun and Earth while the moon is far away, the moon is going to appear smaller. If the moon is smaller, it may not be able to cover up the entire surface of the sun. And if that happens, you get this very rare type of solar eclipse. This is what is known as an annular solar eclipse. Remember that we just saw that sometimes the moon looks smaller? Well, if the moon is big, it can cover up the entire sun. But if the moon is far away from us, it's going to look smaller. It may not be big enough then to cover up the entire sun. And instead, what you get is the moon in front of the sun, not big enough to cover up all of it. You get what we would call an annular eclipse. It's a very specific type of partial eclipse. So you can still see the sun, but not all of it. If you have what's known as an annular eclipse, where the moon is far enough away that the umbra doesn't reach planet Earth, you're going to have the umbra, you're going to have the penumbra, which is a partial shadow. Part of the sun is being blocked. And then you have a new word. It's called the antumbra. The antumbra is the shadow that is falling on Earth from an annular eclipse. This would be the umbra, but the moon is too far away for this umbra to reach Earth. Instead, you get what's known as an antumbra. So we have an umbra, a penumbra, and an antumbra. Another thing that you guys need to know is what's known as the path of totality. If you have a total eclipse, all of the sun is being blocked. But as the moon is in front of the sun, Earth is rotating. As Earth rotates, that shadow is going to fall on a different part of the Earth's surface each minute. And what ends up happening is that shadow will move across the surface of planet Earth because Earth is rotating. That path that the shadow takes is what's known as the path of totality. If you are inside of this path of totality, that means that the shadow of the moon will end up falling on that portion of planet Earth's surface. And as the Earth is spinning, this is going to seem to move. We call that the path of totality. I would like you guys to sketch a solar eclipse for section 2 in your science term. I want you to label all of the different parts. This is a fun little thing that I can play around with. And you can move the Earth, you can move the moon however you would like. It doesn't have to stay in an orbit. You can see that there's a shadow behind the moon, there's a shadow behind Earth. And if the moon travels in between the sun and the Earth, its shadow is going to fall on the surface of Earth. This would be a total solar eclipse. As Earth moves, that path of totality is going to go from one part of the Earth to the next. If the moon goes around Earth once a month, why does this not happen? Why do we not get a total solar eclipse every single month? The answer is that the moon does not go, if you guys are the sun, so we're going to be in a very straight, direct line, okay? You guys are the sun. The moon does not travel in between the sun and the Earth all the time. It is not on the same plane. Instead, the moon's orbit is tilted. So the moon is often up here. Sometimes it will travel like this. You will get an eclipse. But a lot of times, what's going to happen is the moon will cross over in front like this. And if you guys are the sun, there's no shadow that falls on the Earth. So because the orbit is tilted, the shadow is often not going to fall on planet Earth. That's what I just said. Light is always going to come from the sun in the same direction. And if the moon is above that plane, the plane of the ecliptic, then the shadow of the moon is going to miss Earth. The shadow of Earth is going to miss the moon. We're not going to have a solar eclipse or a lunar eclipse. Every once in a while, though, the moon will cross in between the sun and the Earth in that same plane. And when that happens, we'll have either a solar eclipse or a lunar eclipse. This is a little to-scale representation, and as the moon is orbiting, we can change the speed. It looks as though it might go in front. That would be an eclipse. However, let's speed that up. Are we going to get a lunar eclipse? Yep. The moon passed behind Earth, so it would have been in Earth's shadow. But you can see that its orbit is tilted. So the next time the moon comes around, is it going to be an eclipse? Nope, completely missed. Let's see if it's going to be an eclipse. Nope. And we'll go again. We miss. If you take a look at this little box, the moon's not even coming close. So many months are going by. There's no eclipse. Ooh, that was close. That was close. Let's see if we get an eclipse on this one. Looking good. And there's a solar eclipse. That was almost a year later. The moon had gone around, I think, 10 or 11 times. So because this plane that the moon orbits in is tilted from the plane of the ecliptic, which the Earth orbits in, most of the time, the moon is going to completely miss casting its shadow on planet Earth. I want you guys to answer this question. And now I'd like you guys to make an educated guess. Looking at this photo, what do you think a node is? N-O-D-E, a node. Well, we just learned that the moon orbits in a tilted orbit compared to what the Earth orbits around the sun. And if the moon passes through that plane of the ecliptic, you guys are the sun, oftentimes the moon is either going to be above the plane of the ecliptic or below the plane of the ecliptic. When it passes directly through that plane, if you guys are the sun, this is the plane of the ecliptic right here. As it passes from above to below, that's going to be a descending node. And then on the other side, as it passes from below to above the plane of the ecliptic, that is an ascending node. If it's going down through the plane of the ecliptic, it's a descending node. It's going up through the plane of the ecliptic, it's an ascending node. And right there, that is the descending node, because the moon is passing from above the plane of the ecliptic to below the plane of the ecliptic. And it did not happen when it was in between the Earth and the sun. It's not going through a node, so the shadow missed Earth. Here is an ascending node, going from below to above, but it's not in between Earth and the sun, so that will not have an eclipse. What do you want to look for during an eclipse? What are the different stages of an eclipse? One thing that you want to watch out for is the sun. Never look at an eclipse. Ever, 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 ever. Never look at an eclipse unless you have one of these. These are special eclipse viewing glasses that filter out about 99.9% of the light. If you don't do that, the amount of light going into your pupil and hitting your retina will overload your nerves and could end up damaging your nerves and causing you to go blind. Please do not look at the sun unless you have one of these. If you were all in class, I'd hand you each one of these. We'd go outside and we'd look at the sun. But we don't have that option right now. First contact is the very first moment that any part of the moon starts to cover any part of the sun. You guys are now on planet Earth. You're looking at the sun with some special glasses. Right now there's no eclipse. Just as soon as the moon starts to cross over, the first moment that any part of the sun is covered, that is known as first contact. So as soon as the moon just makes contact with the limb of the sun, that is first contact. Second contact is right when the very last little bit of the sun is visible. First contact is right at the beginning. Second contact is halfway through, right when there's just a little tiny bit of the sun still visible. As this is going on, there's going to be some cool stuff. You're going to see what's known as a diamond ring. Because the sun is so bright, the way that our eyes gather light, that little bit of brightness is actually going to outshine all of the rest. And you get this effect that looks almost like a diamond ring with brightness and then one very bright area. You also get Bailey's beads. I want you guys to make an educated guess. Why do you think you get these bright spots showing up? What could possibly be causing that? Turns out these are mountains and craters on the surface of the moon. If you take a look at the moon, you can see that there's impact craters all over it. And as the moon passes in front of the sun will shine through those craters and be blocked by the mountains. The sun is so bright that it causes these little, almost like the diamond ring effect, these beads to show up. So Bailey's beads are an effect of the moon having mountains and craters. In a couple of weeks, we're going to start looking at the sun, different layers of the sun. One of them is the sun's atmosphere, known as the chromosphere. Chromo means color. And the sun has an atmosphere that is completely invisible because the surface of the sun is so bright. If you cover up the light coming from the surface, you can actually see the atmosphere of the sun. We did not even know that the chromosphere, the atmosphere of the sun, existed until we started looking at solar eclipses with telescopes. So we've only known that this part of the sun existed for a few hundred years. And if this is the chromosphere right at the surface of the sun, extending out many millions of miles is the corona. Very, very thin outermost layer of the sun. You can't see it. It is completely invisible if the sun is not being blocked, because the sun is so bright that it will outshine this. Even just a little bit of the sun is so bright that it will outshine the corona. The only time you can ever see this is if all of the sun is being blocked. Then you can see the corona, which is really just a bunch of ionized gas. Ionized gas is going to glow, and that's what we're seeing. You can also see what are known as solar prominences if you have a telescope. So a prominence is something that sticks out. And the sun has a bunch of those things. It actually turns out that the sun is erupting and shooting out material into space. We're going to get to what effect that has on Earth, what that's called, but you can see these little things shooting out from the sun only if you cover up the bright surface of the sun. And then we have third contact. Third contact is right when you get some of the sun to come back. And fourth contact is the very last instant that any of the sun is being covered up. I will tell you guys, this right here is the most dangerous part of a solar eclipse. And the reason is that if you have this, it almost seems nighttime. Animals that are nocturnal will start to come out. The temperature drops. Crickets start chirping because they think it's nighttime. A lot of people are very tempted to look at a solar eclipse without one of these. And I'll be honest, if you look at this without one of these, you're going to be fine. Because it's not the corona is not bright enough to hurt your eyes. The problem is that because it's almost nighttime, your pupils will dilate to let in as much light as possible. And as soon as this happens, that little tiny section, this picture doesn't do it justice, this little tiny section is so bright and your pupils will be dilated that they will overwhelm all of the nerves in your eye, and this is where people start losing their vision. This second right here, this exact instant where the moon moves out from behind or out from in front of the sun, this is so bright and many people are staring at the sun at that moment. Boom, blindness. Please never look at an eclipse without one of these. The hard part is you don't know exactly when this is going to happen. Unless you have a computer that can calculate how long it's going to last, you don't know when that's going to happen. This is where people go blind. These are all of the solar eclipses that happen in the last 20 years. You'll see that there's not a whole lot of them. You have total eclipses in blue. You have annular eclipses. Those are the ones where the sun can still be seen around the outside. And then you have what are known as hybrid eclipses. The heck is a hybrid eclipse? Remember that the path of totality is going to move along the surface of Earth. And if you see a total solar eclipse in one part of the Earth, well, if the path of totality goes to another part that's farther away because Earth is curved, it's possible that some people on Earth will see this as a total eclipse. Other people on Earth will see this as an annular eclipse. So it's both. Those are the hybrid. Those are actually really, really rare.
A solar eclipse happens when the moon's shadow falls somewhere on the surface of Earth. And a lunar eclipse is the opposite, when the Earth's shadow falls across the moon. Total eclipses occur within the darkest part of that shadow, the umbra. In the lighter part of the shadow, the penumbra, we get partial eclipses. So that's the short explanation. But you might wonder why we don't get eclipses every month, given that the moon orbits Earth every 29 days or so. The first reason is that the moon's orbit path is not in line with the Earth's orbit around the sun. It's tilted 5 degrees. That doesn't seem like much, but keep in mind that the model we're showing to you is way off. If the Earth and the moon are this size, the distance between them should be around 10 feet. So at this distance, 5 degrees is enough to keep the moon's shadow off of Earth and the Earth's shadow off the moon most of the time. So why do we ever get eclipses? Because there are 2 points where the moon's orbit crosses the sun's plane, called nodes. And as the Earth moves along its orbit, these points line up with the sun about twice a year. If the moon is between the sun and Earth at that time, we get a solar eclipse. If it's behind Earth at that time, we get a lunar eclipse. In a total solar eclipse, the moon completely covers the sun from the vantage point of someplace on Earth. This is possible because, by coincidence, the sun and the moon appear to be the same size in our sky. While the sun is 400 times bigger than the moon, it's also 400 times farther away. The moon has an elliptical orbit though, so its size varies about 12% throughout the month. At its closest distance, we can get total solar eclipses, but when it's farthest away, we can get annular eclipses, where a ring of sunlight remains around the moon. In the far future, Earth will only get annular solar eclipses. We know that because Buzz Aldrin and Neil Armstrong left mirrors on the moon in 1969. Astronomers bounced lasers off those mirrors to measure the moon's distance, and that's how they found out that the moon is moving away from us about 1.5 inches every year. So at some point in the future, we're talking like 600 million years from now, whatever creatures live here will witness Earth's very last total solar eclipse.
We can see on the radio on the screen a fantastic total solar eclipse taken from the pictures above the clouds.
Den Chef der Sternwarte, was fühlt man in so einem Moment, Herr Philemon?
This is just fantastic.
The totality lasts no longer than 7.5 minutes, and although Earth gets an eclipse like this every 18 months on average, each one is only viewable by less than 0.5% of Earth's surface. Eclipse chasers will travel all over the world to put themselves in the path of that shadow.